In the last episode, we introduced the idea of word to vec. Much to my chagrin, I don't think I mentioned the more general name for models like those produced by word to vec, word embeddings. It's a great term actually because it stresses the process that a neural network computes. Take a word, or a bigram or an n-gram or whatever, and map it, or I guess I should say embed it, in a purely numerical space. Now, one of the things we didn't go deeply into in that discussion was how most effective word embeddings are trained on extremely large corpora. And in truth, very few people will train their own word embeddings from scratch. Most people, like me, don't do that. We benefit from leveraging the embeddings produced by others who have access to both the large corpora and the compute it takes to compute the word embedding. Their resulting output is a model, which, to be perfectly frank, as handy as it is, it's also a pain to deal with due to its size. A useful embedding often takes up a very large amount of memory, and it can be prohibitive to side projects and small startup ideas and stuff like that. I myself have a cluster of 2 servers sitting around with the exclusive function of processing a request to convert tokens into these embeddings as a service. And I actually expect I'm going to need more servers in that cluster at some point, but that's good enough for now. Yet, as you can imagine, there's definitely a use case to find a smaller word embedding, one that might exist on a more practical size server, or even be included in something like a mobile app. That, in fact, is a use case you'll hear about in the second half of our show today, when I speak to Kevin Patel about his work exploring the lower bounds required on the size of a neural network to produce a useful word embedding. But before we get into that, I'm excited to bring you an interview with Marc and Wendy from Microsoft Research, whom I met in Montreal late last year at the NeurIPS conference. They share some details about an exciting competition called Text World. Now, I know from our listener surveys that much of the audience is just a bit too young to appreciate the text adventure game era, so I want to encourage all of you to check out the wonderful documentary Get Lamp by producer-director, the one and only, a man I greatly admire, the greatest living archivist, Jason Scott. I'm old enough that I caught just the tail end of the text adventure craze myself, and I'm thrilled to find out that the Text World project has brought back that form to the forefront as a platform for reinforcement learning research. I recorded this interview a bit ago, so some of the comments about, dates in the calendar things are a bit time shifted. The Text World competition is well underway, so if you're interested in participating, pay attention to our interview and follow the links we mentioned that are also in the show notes. Okay, let's get into it.
My name is Marc-Alexandre Côté, and I'm working at Microsoft Research in the Montreal lab.
And I'm Wendy Tay. I'm a program manager also at the Microsoft Research Montreal lab.
Well, today we're going to talk about Text World. To begin with, can you tell the listeners what is Text World?
Text World is a text-based games generator, and for people that are not familiar with text-based games, those were really popular in the 80s, where you have a screen and you have a description of the environment, might be a room, and you need to figure out what you have to do. And the way you interact with the games is usually through text commands. So you actually have a terminal and you have to type the commands in. So TextWorld is a generator and a framework to study artificial intelligence in this setting, the text-based settings, essentially.
And when you say it's a generator, does that mean you're automatically generating the games, or what's being generated?
Yeah, so the games are automatically generated. This is a way for us to ensure that we can control the complexity of the games, because games that were made in the 80s are really targeted for the humans. So they are really hard for an artificial intelligence to come up with trying to solve it. This is mostly because there's a lot of common sense reasoning that is required when you play such games. The way we built our text world environment is by just reducing the quest length, or maybe reducing the number of objects you can interact with, and also controlling what are the common sense that is needed to solve the games.
So are people able to play these games and have that experience, or is it strictly sort of a machine garden of competition?
People can play it. But it's probably really boring for people because it's meant for machines. And like Mark was saying, the kinds of games that people enjoy playing are just way too complicated for machines. So we've really tailored it that it's possibly achievable for machines to solve. But that being said, I mean, people were playing it at NeurIPS, and I think those who were not used to the text-based game environment found it challenging.
Can you tell me about the origin of the project and why this got kicked off?
So Textwell came as a moonshot project, actually, a moonshot project, where we were trying to figure out what will be the best way of measuring the comprehension of artificial intelligence. So in our group, we are really big at dialogue systems, but it's really hard to come up with an RL agent that we can actually evaluate in a meaningful way. So there's some proxy evaluation like the blue score, but that doesn't tell you really if you understand correctly the context of a question or your environment. And text-based games seems really natural in that way, where to perform well, you really need to understand the context where you are, the room, the location, what are the objects, and also figuring out how to act efficiently in this game, in those games. And a big part of those games is planning. So you need to figure out what is the goal of a game. So usually you are thrown in a text-based games and you know nothing about it, and you need to ask or query the games through text commands to figuring out what's the end goal. And this is like a good parallel with the dialogue system, where if you have a chatbot support, you need to figure out what is the issue that the customer might have, and how best you can assist him.
Yeah. I think the goal of trying to really push the limits of intelligent machines is using something like text world is really interesting, I think.
Yeah, and I will add that Textwell was a design, like why we decided to build our own text-based games, as I mentioned previously, is to control the amount of knowledge and the complexity of the games.
So, can we talk a little bit about the challenge that coders would have in getting involved in this? Text based games, at least my experience with them, is that they're very open ended. You can say anything you want. It might not work or do anything, but you can try it. And it's a lot less obviously linear than other games. I imagine this makes some added challenges for some of the researchers wanting to participate. Can you talk a little bit about the structure and challenges that you'd face if you want to get involved?
Right. So if you are designing an artificial intelligence to play those games, yes, it's really difficult to get a good agent that will be able to perform well in those games. The main reason is, like you mentioned, it's an open world, and you need to figure out what are the correct commands that need to be performed in order to solve that. And this is actually a big issue that the reinforcement learning community have, like when the action space, so the action that are technically possible or doable in a given environment, when it's unbounded. So right now it's essentially just a sequence of words put together, and you hope that it will actually do something in the game. So this large action space is one of the core challenges that the RL community is facing at the moment. So textual games where we can actually control the size of the action space help us to understand the efficiency of such algorithm, like the RL agent that will try to solve those games.
So is there a fixed list of vocabulary available, or can I literally have my agent type anything to the game system?
In theory, anything can be typed. So any sequence of characters, so it doesn't have to be English words, can be French words, for instance, is accepted by the game. But of course, like a lot of them won't do anything, and you will receive like a generic feedback message saying that I don't understand what you are trying to accomplish, or something like that. And so we have a competition that we recently launched. In this competition, so we provide the participant a list of games that they can use to train their agent. And we also provide a list of words that will be understood and recognized by the parser. Essentially, if you stick with this list, you should be fine. So you don't have to use the whole English dictionary.
So if I wanted to become a part of that competition, from a technical side, what does it take for me to get from the starting point to a sort of a hello world?
It's not that difficult to get started, but the complexity comes with building the model. There needs to be some knowledge in, for example, reinforcement learning or machine learning. That's not provided in the starting package.
Sure. Yeah, I mean, obviously, people are going to have to be very clever in the research methodologies and stuff they want to bring to the table. In terms of plugging in whatever that cleverness is, what are the APIs available, or how do I actually interact with the system?
So yeah, for the competition, we have a starting kit where people can see 2 examples of an agent that can be submitted as is if they want. The first one is just like a random agent that will just output random words together. And the other one is from an existing model from the literature called the LSTM-DQN. But they can just study it like the way we built it, and they can train or modify it as they please. Or they can go really out there and try to come up with their own agent from maybe a model that performs well on other tasks, different challenges. In terms of the API, so Textwell also offers this API that will do the communication between the actual text-based games and the environment, the agent. We have all this documentation up online. People can see example of how to use Textwell to play existing text-based games or text-based games made for the competition. Also, to make it a bit easier for the competition, the agent can request additional information. So in addition to the feedback that you receive from the game, you can also ask, okay, what are the verbs that are doing something in the world? What are the entities that I can interact with? Or even what is the list of the admissible command at this current time step? So the admissible commands is simply the list of action or commands that are guaranteed to change the state of the world. So now you are switching to a text generation problem to a choice-based problem. So it's a bit more reachable as a goal. So we do support that in the competition, and we are interested in seeing if people can come up with good solutions for both cases, the text generation and the choice-based.
I imagine there's a lot of different approaches people might take, different deep learning techniques, or as we've been talking about, different reinforcement learning techniques. Of the people who've either shown an interest or maybe been competing so far, have you seen any commonalities in the strategies, methodologically speaking, that people are employing?
So we haven't received any submissions since we opened it last week, and people, I mean, to be able to submit something, you still need to train it on the 4,000 games that we provide. So it takes a bit of time, but hopefully, like in the beginning of next year, we'll start receiving submissions. But in the literature, so this problem of trying to solve text-based games have been addressed before. I will say the most common technique is having some sort of encoder for the observation, and usually it's a LSTM that is used. So just a specific type of recurrent neural network that will try to extract the interesting information from the feedback of the game. And after that, it's coupled with just a simple Q learning approach, like the DQN essentially. So we take the output of the LSTM as the encoder, and we try to predict what is the correct command, like maybe scoring the commands if we have access to those commands in beforehand, or maybe just what is the next word that I should type in.
We are hoping that people don't take a brute force approach, though, or just create something that's totally rule based. We are trying to get away from having agents have or have a lot of prior knowledge. We're trying to really encourage people to build something that can hopefully actually learn the language, learn the environment.
Yeah, with that in mind, can you tell me a little bit about the motivation to start the competition? I know usually things like this will help push research forward a little bit. Overall, why did you guys decide to launch this?
Like you said, it's really to encourage research at this intersection of natural language processing and reinforcement learning. When you propose a research topic in that area, it's such a broad, ambiguous area that it's hard to just come up with what to work on right away. And so by having this competition, it sort of narrows down on a problem that we could all focus on at this intersection of NLP and RL. It also has that text-based game theme, which makes it kind of fun. So that's really just to generate excitement around that type of research.
And how does one win the competition? What does scoring look like?
So the theme of this competition, this first competition that we organize, is around cooking a recipe, essentially. You will start in a world where there's multiple rooms that you need to visit. You need to find a recipe, a cookbook, and from there you need to find the ingredients that are needed for the recipe and process them accordingly. Maybe you need to grill them or chop them or etc. And after that, you need to assemble the meal and eat it at the end. Every time you perform an action that helps you move toward accomplishing this goal, like eating your meal, you receive some points. So every time you find an object that is relevant to the quest, you receive a point. Every time you process the food accordingly, you receive a point. If you fail to do that, you actually lose automatically the game and you will need to start over. And essentially, the score is just how much points you can get across all the games that we have in our validation set. And this is something that is quite new. So, for reinforcement learning, so what we are trying to do is having a dedicated set of games for training and having a disjoint set for the evaluation. So it's not like in the Atari environment where you train and test on the same game. So we are trying to study the generalization of the agent to see if they can come up with some generic algorithm to solve this similar type of quest.
I imagine some of the challenge could be the robustness maybe of the 4,000 training examples you provided. I know those are generated, so they follow some sort of deterministic ordering, even though there's some chance and stochastic behaviors in there. But how do you build that in a robust enough way where they're not just all sort of variations on the same theme that the algorithm can overfit to?
So we made sure that there's unseen words at training time. So you will never see a particular type of food training, but it will be used at validation. We also have longer recipes at the evaluation, different configuration of rooms. So every time you start a new game, the room configuration will be different. So the agent needs to be able to explore efficiently. I think that's pretty much it.
And tell me a little bit more about the competition. I know it recently announced and going to run for a little while. What are some of the timelines and milestones involved?
Yeah, so it runs until May 31st, 2019. That's when the competition ends. Right now, we're in the what we call the development phase of the competition. It's just really to get people started and looking at the training data. But the validation phase, where we'll actually provide some feedback on the agents, starts in January. That's all. Those are all the timelines that we have. But after the competition ends, we'll be having a look at the top submissions, evaluating them, checking the code, and then we'll announce the prizes. And prizes, we have $2,000 USD available for the winning team, along with a 1 hour session, a Skype session with a Microsoft researcher. And we'll determine that at the time of awarding the prize. And then also we'll mention the winner in newsletter and blog posts put out by Microsoft Research.
Well, Mark and Wendy, thank you both so much for coming on and sharing some of the details. Where can people follow up online if they want to learn more?
Go to aka.ms/textworld. There we have information about the competition. You can also get access to the code, and we have more information about the project, such as the researchers, the papers that cite it, and other articles about the project.
Awesome. Well, I'll have that all in the show notes, and let's touch base in a couple months once we see where things end up.
Sounds good.
Thank you so much.
It's not too late to make a New Year's resolution that is both fun and rewarding. What I'm thinking of here is the Brilliant.org Daily Problems. You've heard me talk about Brilliant.org before. It's a great learning website. It interweaves teaching and fun gameplay and activities in nice bite-sized chunks. And every day there's more content, including those daily problems. Each daily problem provides you with the context and framework that you need to tackle it. So it's not just here's a problem. It really helps you learn the concepts by applying them. If you like the problem and you want to learn more, there's a course quiz that explores the same concept in greater detail. If you're confused and need more guidance for that problem, there's a community of thousands of learners discussing the problems and writing solutions. Daily problems are thought-provoking challenges that will lead you from curiosity to mastery, one day at a time. I've always enjoyed the breadth of these questions that cover wide areas in science and math. A recent one poses the question, what's half a Mobius strip? You guys should already know Mobius strip, right? It's the one-dimensional object that has to exist in two-dimensional space. If you've got 5 minutes of your time to invest every day, this is a great place to put it. So what are you waiting for? Go to brilliant.org/dataskeptics and finish your day a little bit smarter. And the first 200 of you that do so will get 20% off the annual subscription to view all problems in the archives. Head over to brilliant.org/dataskeptics.
I'm Kevin Patel. I'm pursuing a PhD at the Center for Indian Language Technology, associated with the Department of Computer Science and Engineering at the Indian Institute of Technology, Bombay.
So I read your recent paper, Towards Lower Bounds on Number of Dimensions for Word Embeddings. And in your own words, could you give a high-level definition of what is a word embedding?
Word embeddings are vector representations of words such that the cosine similarity between the vectors correlate with the semantic similarity between the corresponding words.
Makes sense. And when did you first become interested in word embeddings?
Actually, way back in near 2013-14, when I was beginning my PhD, word embeddings had taken the field of NLP by storm. So much so that the insider joke during EMNLP 2015 was that the E in empirical methods in NLP has now been replaced by embeddings.
So I have always been a little bit bothered myself by some of the seemingly arbitrary choices people make in their hyperparameter tuning, this sort of magic number of 300 nodes or something like that. So
Right.
I was excited to learn about your paper. What was your experience going into this? Were you just following the typical rule of thumb?
So actually, there is something that always bothered me ever since I started reading the papers, because most of the papers during that particular period followed either one of the following specific template. Either they proposed a new method for learning word embedding, or a new application of deep learning where they just say that this is the state of art for some task is X, and then we replace some feature engineering component with some deep learning component Y, and obtain an improvement in the previous state of the art by Z points. But very few paper actually talked about the different settings itself. After some point onward, a few researchers did started focus on evaluating different word embeddings for different tasks, and that is where they started looking at various hyperparameters like the context window length and other features, other aspects of hyperparameters. But yes, dimension is something that was chosen quite arbitrarily, and as you just said, it as a base of rule of thumb in the range somewhere between 50 to 300. So that was already bugging me a lot. And then what happens is our lab, the Center for Indian Language Technology, short for it is CFILT, it consults for many companies and organizations. During one such consultation, a team from a reputed smartphone company, which intended to make an SMS classification application, asks us, look, we want to use deep learning and word embeddings in our app, but we also want the app size to be small, as the users do not prefer to download larger apps. So can we train embeddings with just 10 dimensions? That is where I completely lost it, because not only is the number of dimensions problem being ignored in academia, but also in the industry. And what if such an oversight leads to, say, for example, an emergency SMS being labeled otherwise? So this is where me and my supervisor, Professor Pushpak Bhattacharya, seriously started brainstorming this problem.
So we can begin with a very generous bound and say one hidden node is probably too few,
Right.
and 3 million is overkill. But certainly we can do a little bit better than this. How do you tighten those boundaries?
So actually, the main insight for this came from study of polysemous words. I mean, if you have this basic idea as in vector space, those words which are semantically similar are close to each other in this word embedding space. If you consider, let's say, the word bank, and let's consider the two senses of the word bank, the financial sense and the river bank sense. In the word embedding space, let's say a boat is supposed to be closer to the riverbank sense of the word bank, and the word money is supposed to be closer to the financial sense of the word bank. However, in most word embedding algorithms, different senses of the words are not considered separately. There is only one vector or one embedding per one word. These two senses have been collapsed onto a single point in the vector space for the word bank. And this collapse version indirectly brings the word money and the word boat closer to each other. So from this point, we thought that when two different senses of a word are collapsed onto a single point, it distorts the vector space. The word money and the word boat should have been much further apart from each other than they actually are due to this polysemy. So similarly, what would happen if we reduce a number of dimensions to such a point that even unrelated words start collapsing onto each other? Then that will lead a big distortion in the vector space, right? So this is the major point which we started digging in from.
Prior to your work, what sort of methods existed to evaluate the quality of a word embedding?
So, as far as evaluation of quality of word embedding is concerned, they are really broadly categorized into two methods. One is the intrinsic set of evaluations, and the other is the extrinsic set of evaluations. So, in case of intrinsic evaluations, the most simplest one is this word pair similarity task, where a pair of word is given along with a human annotated similarity score, and the correlation between the human annotated similarity score and the similarity computed using word embedding is found. And if the correlation is higher, we say that the embedding is conforming to the human notion of similarity between this pair of words. Thereby, the embedding is much better. So this is one way of evaluating it. Then there is the classical task of word analogy. If anyone has read a bit of word embedding, they will have stumble across the example of king minus man plus woman is equal to queen. That particular task is another intrinsic evaluation method for the quality of word embedding. And as far as extrinsic evaluations are concerned, that is where you actually use this word embedding in some downstream NLP task, let's say part of speech tagging, name entity recognition, so on and so forth. The performance of that particular task itself is an indirect measure of the quality of the word embeddings.
And I believe you guys brought the original idea to the academic mind of the pairwise equidistance. Is that correct?
Actually, we came up with this very simple idea that suppose we have a certain set of points which are pairwise equidistance, in the sense that suppose we have 4 points A, B, C, and D. The distances among them are such that AB is equal to BC is equal to CD is equal to AD is equal to all the combinations are equal.
So some sort of parallelogram then.
Or rather a regular tetrahedron. So that is the exact message. So in order to draw a regular tetrahedron properly, you need at least a 3-dimensional space. If you move from 3-dimensional to 2-dimensional, you have to inevitably break one of this equidistant constraint. Therefore, if you have 4 points which are pairwise equidistant to each other, then the minimum number of dimensions to embed this or to like have store this four points is 3. You cannot go to dimension 2. So that is the basic idea behind our paper, that given a corpus, if you are able to figure out what are the see, ultimately the word embeddings are learned from the corpus, right, from the corpus statistics. So from this corpus statistics, if we can figure out that okay, there are certain x number of pairwise equidistant points, in fact, that particular number of equidistant points puts a lower bound on the number of dimensions. Just as in the example, since there were 4 pairwise equidistant points, the minimum number of dimension was 3.
And what would happen to my embedding if I made a mistake and I chose too few dimensions?
Yeah, so this pairwise equidistant constraints will be broken, right? And that will end up in distortion of the entire vector space. So if we go back to the example of this polysemous word, right? So suppose the 4 points A, B, C, D were indeed money, bank with the financial sense, bank with the river bank sense, and boat. By making this mistake and by not sticking to that minimum bound and going below that, you may end up with, let's say, this 2 banks collapsing onto a single point and thereby distorting the actual distance between money and boat.
And what would be the drawback if I went the other way and I was too generous with how many nodes I put in my hidden layer?
By generous, you mean to say putting an arbitrary large number of neurons over there?
Exactly, yeah.
Okay, so that is something that we are currently pursuing as to what could be the upper bound on the number of dimensions for word embeddings, right?
So if we just approach this empirically, we could start reducing our hidden layer size and empirically see that result coming out, that the quality would decline. How are you able to use the equidistant pairs to find a more robust lower bound?
The example which I gave of the regular tetrahedron, in that case, the distance measure was Euclidean. But actually, when we use word embeddings, we use cosine similarity, right? given a particular number of equidistant points, what should be the a particular distance, or let's say we are talking about cosine similarity, so it will be more about pairwise equisimilar points in that case. Given a number of pairwise equisimilar points, what will be the minimum number of dimensions of the vector space which will contain that? That is an active area of research in mathematics, pure mathematics. If you see my paper, I have cited this paper from Alexander Barg and Yu, a paper New Bounds for Equiangular Lines in Contemporary Mathematics. So that is one such paper which actively computes this minimum number of dimensions needed for a certain number of pairwise equisimilar points or pairwise equiangular lines, let's say, because we are computing cosine similarity, right? So this is an active area of research where they use lots of different mathematical techniques like semi-definite programming and so on and so forth to actually come up with such values. Table 3 in my paper actually shows a small portion of that particular research. What kind of research goes into this computation?
The algorithm is always going to try and do its best, I guess, just under the constraints you give it. So we don't want to over-constrain it. We want to know that lower bound, and this seems like a nice method to get at it. Can you talk a little bit about the empirical results? I mean, the idea sounds intuitively appealing, but it doesn't have the rigor of like some lower bound complexity theory proof.
Right, yeah.
You can measure it empirically, though. Can you tell me a little bit about your tests?
So there are two things which I would like to say regarding this question. The first thing is, for empirical analysis, what we did was we chose the intrinsic evaluation tasks, that is that word pair similarity, word analogy, and there is also another task called categorization, where we actually categorize words using word embeddings and then find the purity of the clusters. We cluster words using that and find the purity of the clusters, because in this particular task we already have the corresponding labels. So if a cluster has only one label, then that cluster is considered to be extremely pure. Based on how pure the clusters are being formed, one judges the quality of word embeddings in this case. So these three tasks we used for evaluating the quality of word embeddings. And what we did was, for this brown corpus, we started training word embeddings of dimensions 1, 2, 3, 4 up to 35. And then we actually tested the quality of all these different versions of our word embeddings. We checked their quality using these three tasks. For lower dimensions, that is 1 to 10 and so on, the quality ended up being really poor. Then it started stabilizing a bit. And then as soon as we reached dimension 19, from that point onwards, the results didn't change that much, or rather, the results did not change significantly, statistically significantly. So from dimension 1 till dimension 19, whatever jumps were observed in the improvement in the evaluation, the quality evaluation, those jumps were statistically significant. But after 19, the jumps were no longer statistically significant, they were purely random. And on the other hand, when we actually found the number of pairwise equidistant points from the brown corpus using the method which we have described in the paper, and that number ended up being 62. And using the tables from the paper, like the one which I talked about, that Alexander Barg's paper, we observed that the corresponding minimum number of dimension for 62 pairwise equiangular lines or pairwise equisimilar points is indeed 19. So that is
Wow.
how we ended up with this particular bound. And the corresponding, we also have a empirical observation for confirming this result. What we are saying is that the vector space with 19 dimensions is representational enough to capture the corpus statistics. If we go below that, we don't have that much representational power in that particular vector space.
So that finding is based on the brown corpus. How do you think that will evolve into different corpora, especially maybe larger ones?
While there is nothing that will say that the trend will not follow, unless we are able to actually run max click on larger corpus and get the actual value, it is difficult to say. But this is something that plagues not only our paper but even other works. So, for instance, this other paper which I am talking about by William Gus and Ruslan Salakutdinov on characterizing the capacity of neural networks using algebraic topology. This is also something which we were trying to do, but we were not, or rather, these guys beat us to it, where they actually use something known as persistent homology from algebraic topology to compute the number of the neurons needed on different hidden layers of the neural network. So that is an interesting direction that we will also be pursuing. this algebraic topology paper. Even in that, computing persistent homology is an NP complete step. So most of the work which I've seen in this particular area have something or other of this sort, and that is why we are only able to comment on, let's say, toy sets and toy corpora only. But would like to see as to how they will, whether the same trend will follow in the larger corpus or not.
I'm wondering if there are any, polynomial time approximations of the clique problem that could be useful in lieu of, solving it exactly.
What we did was we tried 2 or 3 different approaches. We also tried using SAT solvers and other things. But maybe the problem instance for larger corpora is too big for even SAT solvers to finish it in time.
What advice do you have for practitioners, people that are going to go out there and build their own embeddings? How should they measure their corpus, and what can they take away in terms of informing the right size for their network?
So one thing which we had often discussed in our lab too is that while we may not be able to figure out the exact number of pairwise equidistant points from any given corpus, but for a particular task we may have a set of words from our linguistic knowledge which we do need to maintain their distance constraints. So for instance, I will give another simple example. Let's say we have some let's go back to the older days of feature engineering, when let's say we have some 2 or 3 features, let's say like is an animal, is a pet, is a 4-legged creature or something like that. And based on that, if we have certain animals, let's say dog, tiger, a parrot or so, and then maybe we can say that okay, dog and tiger are pairwise equidistant because they are animal and they are 4-legged. Okay, and dog and parrot are same because they are pet and you get the idea, right? So the point is, if there's some linguistic knowledge of this sort, maybe we can use that set of words and say that okay, in my set of words there are 50 words, so maybe my minimum number of dimension according to this table should be 16. This kind of knowledge could go into practitioners or can be used by practitioners, and that is one of the, let's say, points of the paper.
And what's next for you? Is this one step in a long line of research, and how does it fit into your overall PhD program?
Right. So actually, I'm investigating both this lower bounds and, as I said earlier, the upper bounds on a number of dimensions of word embeddings. And we are also looking at not just word embeddings of this, which are basically trained from a language modeling perspective, but whether, let's say, from a machine translation perspective, does the same thing hold or not. And I'm also looking at certain different types of word embeddings. So, for instance, you must have heard about interpretable word embeddings.
Sure, yeah.
Like as opposed to ordinary word embeddings, in case of interpretable word embeddings, an individual dimension does make some sense. You can figure out what an individual dimension captures by sorting the words based on that particular dimension in descending order, and then looking at the top few words that actually does show what that dimension mean. We are looking at this bounds on even in case of interpretable word embeddings also, and also investigating as to so if you recall in the beginning, I told about the SMS classification application and what sort of errors could lead to certain troublesome let's say decisions, right? So for instance, you must have heard about the GDPR, European GDPR, and along with other things, it brings about this right to explanation. How do word embeddings, what kind of role does word embeddings play in, let's say, explaining the decisions of neural network based models? That is also something that I am currently looking into.
Well, I wish you the best on that line of inquiry. I'm very excited to see what you discover. Any final thoughts before we sign off?
So just shout out to my colleagues and my PhD supervisor, Professor Pushpak Bhattacharya, for guiding me, and of course to you and your team, Kyle. Thank you for giving me this opportunity to discuss my work on your platform.